Hey everyone, I'm Brian, and I'm going to talk to you about a summer project I did with NRAO on an RFI database. So the layout of my talk is answering the what, the why, and the how, and then the what is that RFI contaminates radio astronomy data and that more of it is coming. Why do we care is because our current mitigation tools are limited and inefficient. And how we propose to address some of this is through an RFI monitoring framework and database. And then I'll go into our experiments from the summer with this initial sampling and database prototype. So what is the VLA? The VLA is a 27 element array which produces images of the radio sky at a wide range of frequencies and resolutions. And the basic data produced by the VLA is what's called visibilities, or measures of the spatial coherence function, which is formed by correlating signals from the array's elements. And the most common mode of observing will use these data to form images of the radio sky as a function of sky position and frequency. There are 8 receivers with continuous coverage from 1 to 150 gigahertz on the VLA. And another way to think about the VLA is that it's a very sensitive RFI detector. So RFI contaminates our data and makes everything from calibration to extracting scientific results difficult if nothing is done. And the VLA's current way of dealing with RFI is to look at the end data products after all the signal processing is done and to throw out anything that's contaminated. So the plot on the right you see is L-band, and all those spikes, all the black spikes are RFI. Not only are the spikes removed, but all the data in those channels are thrown out. And with these handling methods, this results in losses of about 40% at L-band, 30% at S-band, and about 20% at X-band. So between 1 and 5 gigahertz, the VLA loses up to 30% of its bandwidth in continuum modes. And then the forecast for the future is not looking so bright. So too bright. ngVLA 48, Memo 48 outlines several categories of emitters that are expected to impact ngVLA the most. So the main categories are vehicles equipped with radar, 5G telecommunication, Internet of Things, such as your Bluetooth devices, medical implants, cell phones, ground-based radar for aircraft communication and surveillance for civilian and military purposes, drones, things like that. Last but not least is satellite constellations, things like SpaceX and OneWeb, and these will dramatically affect radio astronomy. So the number of satellites currently approved by the FCC is on the order of tens of thousands. So in general, RFI is going to be more frequent. It's pushing into higher frequencies. It's going to occupy more time and more frequency bands, and it will do this all with higher peak power. So the RFI environment between 10 and 100 gigahertz is expected to be similar to what is seen currently between 1 and 4 gigahertz. So if we were to use the existing method of identifying RFI in post-processing and throwing it out, we will throw away 20 to 35% of the entire ngVLA observable spectrum, and it could render entire parts of the spectrum inaccessible. So the question is, what can we do about this? The first line of defense is policy and protecting scientifically valuable frequencies. And this is done through spectrum management and projects like the National Radio Dynamic Zone. Another thing we can do is avoidance, such as in smart scheduling, and then efficiently planning observations around RFI once we know when and where it comes from. And then as for dealing with RFI once it reaches the VLA, the RFI forecast was able to form categories based on the characteristics of the expected RFI, such as which bands, time scale, duty cycles, and so on. So having these categories help form the mitigation strategies. So we can leverage the characteristics to intercept RFI at different stages in the signal processing. So one of them would be looking at raw voltage streams to detect wideband RFI per antenna. The next would be looking at real-time spectrum to detect narrowband RFI. Another one is looking at correlated baselines in high time and frequency resolution to see if there's recoverable data. And then looking at average data in post-processing for weak RFI. So in general, these stages provide better time and frequency resolution about RFI that we could use for either removing RFI at that stage, or they could be used as detection stages to better tune other algorithms downstream. So for example, if incoming RFI is wideband or narrowband, and a cost benefit analysis was done in Memo 70 and showed that using these other stages may be an effective tactic against different types of the expected RFI. So an ngVLA technical concept was put forth that proposed for a database for RFI emitters. So that database would support developing the previous ideas and enabling other key capabilities. Basically, having a database and collecting information about RFI emitters, we can monitor the environment to inform policy or spectrum management or spectrum managers if there's infringement on those bands. It'll answer the questions if the RFI environment is suitable to doing high resolution flagging in the correlator. Like, is there enough space between duty cycles for usable data to warrant high resolution flagging? Currently, that's unknown. And then metadata would support developing algorithms that model and subtract RFI, so one could potentially recover sky signals from underneath RFI. And then by keeping metadata at individual antennas, we can better study the amount of decorrelation that's happening in processing. Basically, the takeaway here is that the database creates a feedback loop for learning. So better characterization leads to better algorithmic tuning, which leads to better removal or avoidance. And then implementing these strategies will redeem observation time and bandwidth across the spectrum while minimizing imaging artifacts. And the VLA is a sensitive RFI detector and basically an ideal testbed to start these experiments. And thanks to Alan Erickson at NRAO for creating an RFI monitoring framework and database prototype that already exists on the VLA. So this is a real-time system that taps into the array's antennas. So this metadata is recorded in a Postgres relational database, and it collects basic data about the observation, such as which facility, like the VLA or the VLBA, the timestamps, pointing, position, local oscillator or intermediate frequency setup, which hardware is used for collection, and then it also stores metadata about the RFI detection itself, like peak location, width, power, which algorithm was used to detect it, and much more. So this framework samples the voltage streams, computes real-time spectra, and uses a simple detection algorithm to find peaks. And then when it does, all that metadata is recorded in the database. So this is the framework and initial database that we used over the summer to carry out our experiments. And our first test was to see if we could take the data recorded in the database and turn them into a CASA flag file. So a flag file is simply a list of commands that indicate which data is to be removed from further processing. So we wrote software to read the data in the database and write a flag file automatically that can be used in CASA calibration. And the goal of this would be that you get RFI specific to your observation rather than using a stale monthly table and then the database would automate the process of identifying and removing RFI from your data sets. The first test was to see if we could use the existing entries in the database to create the flag files that could be imported to CASA. So initially we grabbed all the entries for an observation, but this resulted in thousands of flags, and then not all of them were useful, such as when the telescope is slewing between objects and positions. So we then had to go into the measurement set metadata, pull out the scan times and the frequency ranges to then further refine the SQL queries to the database. And then once that was done, we were able to try again and see what the flags created. So the red dots here are what was created from the database entries. And while we did create and get the flag file to work, the peaks in the database didn't match well with the RFI and the cross-correlated products. So we focused our attention on the algorithm doing the peak detection in the sampling prototype. So we ended up swapping the existing algorithm for a simple statistical threshold model, and then the plot on the right is an example of it on synthetic data. The blue dots or the blue stars you see are signals deliberately put in, and the red dots show what is detected to flag. There's a 1 sigma level difference between noise and the inserted signals. And then on these particular settings, it has a 100% accuracy rating, but almost a 20% false positive rate, which is pretty aggressive. And then for this same algorithm on wider RFI, the widths are calculated and applied. That's just shown in red there. And that's a mix of narrowband and wideband features in this synthetic data set. This algorithm isn't perfect and could certainly benefit from more tuning, but this gave us a sensible baseline to start with for the rest of the prototype. And this here kind of highlights the benefit of observing and keeping metadata, because if you know what to expect, you can tune algorithms to be much more effective. And in general, I think I'd like to point out that we aren't limited to only using one algorithm. So in the future, the idea is to have many different algorithms running simultaneously, scanning for RFI and reporting information to the database. So the digital signal processing path for the VLA, from a very high level view, is that the antennas observe voltage streams. Those signals are shifted to basebands for amplification and for preparation for compression. Then there's an analog digital converter that works at a rate of 60 megabytes per second or 216 gigabytes per hour. Those digital signals are then passed to cross-correlation to compute the power, reduce noise, and align phase. And then it goes on to post-processing for gridding visibilities, calibration, imaging, and so on. Where we tap in is directly after digitization and split out the signal from there. So we sample our data stream after digitization but before cross-correlation. And while the digital converter digitizes at a much faster rate in the gigahertz range, we sample the stream to a bit rate that is easier to process. So we sample the data stream, we compute fast Fourier transform to get a spectrum, and then run the peak detector algorithm. Any peaks are then logged into the database with the metadata. And here is an example of what the time average voltages look like. This is what we're pulling from the data stream, and then this is also an example of what is going into the correlator. You may be able to pick out some RFI features here, but they really stand out in the spectrum. So these are those same 4 examples. And we take the average time values and compute the Fourier transform on the fly to get the spectrum. It's notable that since there are two baseline boards, it's possible to get two spectrums, and depending on tuning, we can get slightly different spectrums. Also, because of where we sample the data stream, the bandpass is still present, as you can see kind of on the edges of these spectral windows here. And then the red lines are what the peak detection finds and writes into the database. So one major thing to see here is that we are not time correlated between antennas. So we're doing peak finding pre-correlation and trying to flag in post-correlation, which isn't fully determined yet. So we're using the raw timestamps, and we're not using signals that have been phased up in the correlator. So without this time correction, an RFI spike may show up in a channel or two over from what we detected after correlation. So there's some work to be done for extra bookkeeping that needs to be figured out and recorded if we want to flag pre-correlation. So the major takeaways here are that flagging pre-correlation could require better clock accuracy, and this may be a motivating reason to sample the data streams at the correlator level. And then the what spikes that we're seeing in these voltages aren't showing up in the visibilities post-correlation. Excuse me. We suspect this is due to the decorrelation of RFI, and this is a topic Urvashi Rao is currently working on to answer this very important question. And with that, I want to say special thanks to Prashant for mentoring across time zones, and to Alan for all his work setting up the framework and prototype and helping us along the way. And with that, I'll end my talk and leave the slide up while I try to answer your questions. Thanks.